In this video, we're going to do example 6.2.4, where we're given a triple integral over a solid S in one order. We're asked to sketch S by looking at the bounds and to rewrite the integral in two other orders. So let's go ahead and look at the outer bounds. X goes from 0, so x equals 0, to x is equal to 1. The middle bounds are y, so 0 to x squared. So we've got y is equal to 0 is less than or equal to y is less than or equal to y is equal to x squared. And the inner bounds are z, so from 0 to y. Z is equal to 0 to z is equal to y. So let's go and sketch these three solids, well, at least these two, and see what their intersection looks like to give us our solid S. Right? We're looking at the part that is all positive, so the part of the first octant where these solids intersect. So if I look at z equals y is a plane. And if I graph the axes here, so this is the y-axis and the z-axis, z equals y in the yz plane is the line, z is equal to y. But if I add an x-axis, we have no x variable, so our plane is parallel. And so our plane here sort of runs along the x-axis and comes out at an angle like this plane z equals y, like this line z equals y. It's the same plane. So then let's look at y is equal to x squared. Y is equal to x squared. There's no z. And so if we graph this down in the x, y plane, just the positive part of it, anyway, we'll get this parabola. Now, since there's no z, right, we do understand that there's another part of the parabola that we don't need back there. We are going to have a parabolic cylinder. Again, there is part of it back there that we don't need, but we're in the first octant, so we have this parabolic cylinder here. So we can imagine this plane, right? They'll meet down at the origin, this plane coming along the x-axis until x is equal to 1. Yx equals 1, because that's our boundary here. And intersecting, it's going to come up and intersect the cylinder like this, and so we'll get sort of a curve down from this point up to there. So our solid S here is what I've drawn in blue. It's in the back there, it's bounded by the parabola the cylinder y is equal to x squared. On the front we're by this triangle, which is x is equal to 1, and then the back surface is z is equal to y squared. I say the back, it's really on the left the way I've drawn it. But if I draw this, let's say if we take this and let's spin those axes around, you might find it easier to see that solid in this orientation. Either one is fine. So if I change and I put the positive x-axis that way, the positive y-axis this way, so I've just taken those axes and spun them around 90 degrees so that we have another orientation. So then our curve y is equal to x squared comes out something like this. Let's draw it nice and big so that we have no trouble seeing what's going on. This is the point that's right there, so that is the point that would be 1, 0, and so our triangle would have its base here at x equals 1. That's the triangle, the line that I just drew in is that line there. Now, we're going to go up, z is equal to y, if we're going to reach that point up here, so that's going to be the point 1, 1, 1, 1, 1, that's it. And we're going to have the front of our triangle come down like this, and then this side here go down. So this face here is this face here that I've just drawn. And then the surface must go from this point back down to the origin where z equals y meets, and so it's going to be swooping down like part of this, right? It's the parabolic cylinder that's being cut off, so we're going to have this sort of curvy face here. That is the parabolic cylinder. That's what's tucked in behind that face there that you can see. And then in the very back is the surface, right? This part here that I've just shaded in green is that part, whoops, back in here. So I hope that orientation makes it a little clearer, but either orientation is just fine. However, it helps you picture the solid. So we want to switch orders. We want to switch orders first of all to dx, dy, dz. dx, that means we need boundaries in terms of x. So the x boundary, well, the front boundary is going to be this in terms of x. That's x equals 1. So x is equal to 1 is the top. And what's behind, if we're going in the x direction, it's this in red. That surface is y is equal to x squared. But if we need that in terms of x, then that is root of y. So x goes from root of y to 1 through the solid like that. We need those on, I should write that a little bit lower down, we need that on the YZ plane. So I can imagine the projection of this solid back on the YZ plane. Well, it's going to be that triangle. So let's draw that YZ plane. I move this out of the way. Let's draw the YZ plane here. So Y and Z, and this triangle projected back over here is going to give us this, where that is again the line Z is equal to Y. So we can set this up in either order, but we're actually told that we want Z as the one that's going to constants. So that is going to be from 0 to 1. So Z is less than or equal to 0 is less than or equal to Z is less than or equal to 1. And then the Y value, right, for any Z along here, Y is going to go from Z to 1. So Z is less than or equal to Y is less than or equal to 1. That allows me to rewrite our integral using these bounds. So we have instead the integral from 0 to 1, the integral from Z to 1, the integral from root Y to 1 of whatever function that is, f of x, y, z, and the order is dx, dy, dz. So there is the first of the two orders. We're also asked to rewrite in the order dy, dz, dx. So let's take a look at that. Now we want y as the inner integral. So y is going to go from the green surface in the back to the red surface in the front, right? So from the green to the red. The green was z, right? Y is equal to z. So we have z is less than or equal to y is less than or equal to, and in the front that was the cylinder, x squared. Now we need to have this projected back onto, this time, the xz plane. I don't leave myself enough room. Let's move that down. So we now need this back on the xz plane. And you might wonder, well, what is that, this curviness here? How do we solve for that? Well, what do we know? That's the intersection. We're looking for the projection back onto the xz plane. And so this curve is the curve of intersection of z is equal to y and y is equal to x squared. So if I'm projecting that back down to the xz plane, well, z is going to equal x squared. So I have z is equal to x squared is going to be the projection of this back into the xy plane. And so we're going to go here. This is 1 and again 1 here. And we need this region here. And so the question is, are we setting this up as a type 1 or a type 2? We need the constants to be x. So x is going to go from 0 to 1. And then z is going to go from 0 to x squared. So 0 is less than or equal to z is less than or equal to x squared. So that order lets us set up our integral as the integral from 0 to 1, the integral from 0 to x squared, and finally the integral from z to x squared of whatever function f of x, y, z. And now the order of integration was this one, which we can read backwards through our bounds here is dy, dz, dx.